There you go. Yep, that's your Q3 right there. Yep.
Okay, so I'm guessing real fire or not real fire.
Yeah, real fire ceramic logs. Well, we went to choose logs. There were lots of options, but this was the only one that had birch logs. And I liked the color. It was a different, they look different. Most of them look like dark wood. These had look like light birch. So I was like, "Ooh, these are cool."
Want to be different. Oh,
You know me, I'm always trying to be different. Look at my house. It's full of different, isn't it?
and I like to be different too. Like when
Yeah, I'm always on the stairs.
oh
No, that's good. That way you know where it is. This one here for you.
I like that. Like the house that I like to be different too. Like when we're doing group project or like not group project, but when we're doing projects in the old school group, I like to make mine unique.
Oh yeah, you guys did some sewing recently, didn't you?
But I guess I didn't really do anything with that because it was a hat and a scarf and stuff, but usually I like to make things different.
Well, that's cool. Well, I've always been somebody who's tried to make, how did I get kicked off of there? Somebody who's tried to make things different. When I was in school, I went through a period where I didn't match my socks for about 2 years. And this is all because at the time, my mom was going bowling on Sunday nights and she found this bowling league it was called a Big and Little League. It was basically like parents and kids. So it was me and some of my friends and my mom and some other people. We were on this team together. And one day I didn't match my socks and I got my best bowling score ever. And I stink at bowling, so my best bowling score is pretty sad, but anyway, it was my best bowling score ever. So after that, I didn't match my socks for 2 years, and I wore only neon colors for probably 3 years. It was as a thing.
You don't like your socks and
I did multiple years. The first time I actually, when I got to the point where I kind of didn't want to be like that anymore because it was too weird, and I wanted to try and be a little less weird. I knew that people would comment on the fact that my socks matched, so I just avoided socks by wearing pantyhose for a good 6 months till I phased in matching socks. Yeah, I'm weird like that, for real weird. But this is sleepy weather. This is like take a nap day.
I love your good
I do.
since we've had a good rain.
Yeah, Ozzy's afraid of thunderstorms though, so I had to give him his drugs and put him in his room. He doesn't mind the rain, but the thunderstorms freak him out. I did not notice when I put this rat on here that he had 2 tails. Oops. That's funny. I usually catch that's why I was telling Jason. I was telling Jason, my biggest problem with these AI rats is the errant.
Here you go.
Oh, thank you. Thank you. How are y'all?
Say it's a genetically modified rat.
It could be. It could very well be. Okay, in here, guys, are your it's your Q3 notes
Oh.
and your Christmas presents as well. So, we'll give you. Awesome. Very cool. Did you guys have an amazing trip?
Yep.
I'm so impressed. Hey, sweetie, come on in. What's up?
I'm back.
Eunice. There you go. Eunice, take lesson 20 out of your binder and swap it out for this one. Not the lab. The lab's okay, but the lesson I put in was not.
For the lab rats.
No, for your class. Just leave the lab 20 is fine, but the actual lesson 20, for some reason it ran off a copy of
My back is literally so wet.
Yeah, I'm sure. If you want to hang your coat on the stairs, on the rails like Emma's, you can do that. Is it? Yeah. If you have a wet jacket and you want to put it on the stairs, that's fine. Like Emma's, I looped Emma's through one of the little loops on the stairwell. You can do that if you want.
Lesson 20 that you put for the lab rats.
No, it's your lesson. It's your lesson, it's juniors, but just take out whatever's in
We have
there
22 brownie points.
already. Oh, you mean from, yeah, from last time. Yeah, you guys got a lot.
Yeah, how are we? Also, we got one brownie point, like,
Oh, did you find another one?
you're good at finding brownie points.
He's really good at it. There's always
Yeah,
one kid in every class.
This is called reflection, and incoming wave can be called and incident wave.
And,
It's not and, it's an incident.
There you go. You found it. You found it.
Please make sure to add one brownie point.
Okay.
Because you forget to add the brownie point.
Sometimes I do. If y'all write it down, I usually remember, but, and then the ones that you had before, I miscounted. You wrote them down, but that you
It's like a brownie, like whenever someone finds a brownie point, they can write down the brownie point with a stick.
Oh,
out
yeah,
and, like,
yeah.
stick it to the side of
Stick it on here so I remember it. Yeah. Oh, there's Cole.
Yeah, okay.
Cole had an accident
Yeah.
yesterday. Scared
Is that
Cole.
right?
Do what?
I got the phone number.
Using.
You do have it? Do you have Edith's number?
No. I don't.
Okay, I'm gonna forward Edith to you.
Mine's looking, you just have to.
No, because she may have a question and I'm not gonna be able to answer it because I'm already here and I'll be teaching, so.
Well, me, I need Edith, I'm on the shot guy.
Yes.
No, just send it to Edith. She'll, I'll forward her contact to you real quick. All right,
What's the insurance adjuster do again? Adjusters?
they are the ones who will determine how much money your claim is worth.
Okay, so they said she'll they'll contact me tomorrow.
They'll talk to who?
The adjuster will contact me tomorrow.
Contact you tomorrow? Okay.
If the shop just needs to send it.
Yeah, but you have the claim number. You go ahead and give that to Edith. And, good. So were you able to get her first name from the police or from?
No, called the agent's office.
Yeah,
And
okay.
they couldn't actually file the claim, but she said she could look up the number and give the name. Plus, I looked her up on Facebook, it's the same name.
Which is
Cornell?
Cornell. Okay. All right.
That's the first name.
Yeah.
Cornell, cool.
Okay.
Wow.
Miss Danny also found one brownie point, begin lesson 22, no, begin lesson 21.
Yeah, that's all that one too. I saw that one after it was too late. That was like an issue. The reason that's like that is because, the last time I got this class, yeah, Glatzer, yeah.
So let's swap these two with this.
Yeah, lesson 20, just pull lesson 20 out and put the new lesson 20 in. And you're good, perfect. Yeah, Cole had a lady run a red light yesterday and he was going through the intersection with the green arrow turning left and she ran right in front of him. And he couldn't see her coming because there was a bus and she blew past the bus and he took the whole front end off his car. But as you can
Gnarly,
see,
right?
hey, look at that, guys, right? And this car is like, this is his baby, so.
It's out of fun, it runs fun.
Yeah, we drove it to Marietta. Well, he drove to Marietta yesterday because we have friends that own an auto body shop in Marietta. So I immediately called, I know, it was perfect. So I called them while we're standing there on the side of the road with the car and I'm like, we have a problem. He has to leave for Texas on Sunday and he has no front of a car. So, they said they would get it fixed. They said they had 140 cars in the shop, but they were moving him to the head of the line. That's what friends do. So
Like
be good to your friends.
my dad, people at Zaxby's know my dad very well.
Oh,
We
yeah?
were invited to their Christmas party, their company Christmas.
How did they know your dad? Just because they own it or?
Because they didn't know each other outside of Zaxby's.
Oh,
My
your dad
dad
just goes there all the time.
Yeah,
I'm surprised Jack didn't get invited to the Subway Christmas party, you know?
yeah, but my dad will get like move to the front of the line, like they'll get him first. and
That's
do
nice,
extra
because it's
things.
always there.
Sometimes one of the employees will give him half of the employee discount.
There you go.
Yeah, so we're very friendly with the Zaxby's people.
Yep, yep.
And Larry.
So when you're out there driving around in the next couple of years, when you guys get your licenses and stuff, always watch for people coming through red lights that don't belong coming through red lights. Like, he couldn't have seen her. There was nothing. Get this is his luck.
So it was right over by, there's a school there, so there's always an officer out there like directing traffic. And the officer heard it and looked and saw that she had the red light, so there was no arguing like, hey, y'all, welcome back. Darcy and Lewis, if you will swap out your lesson 20 for this lesson 20.
Oh, you did?
Okay, this lesson 20 is the right one, the one in your binder was wrong, so if you can swap it out.
Miss Danny?
Yes,
I lost my Q3.
all of it.
Yes.
We photocopied lesson 18.
Oh my goodness.
So you put this here?
Our dad must have thought it was old.
No, I lost it.
Okay, I can get you new ones. I'll get them for you next week. Does that work? Send me an email if you remember in case I forget, just in case, since we're starting.
Because it's so dorm.
Yes, it's dark outside.
Dorm here. It
Oh.
feels so cozy. I woke up today and I'm like, I thought it snowed, but it was just like.
You know, last night we were outside and it was like 39 degrees and it was spitty and I thought it was gonna be sleet on our drive back from Marietta. So fortunately it
It
wasn't.
was like 23 degrees when I went to sleep.
Yuck. All right, well, Happy New Year, gang. We are here. We are moving into Q3.
15 next year.
Now are y'all with me? So I noticed just this morning, get this, that this is another rat with an errant tail and I didn't catch it before that. Isn't that funny? That's the one thing AI does that I have the biggest problem with, is it adds like an errant extra tail. Sometimes the tail's not even attached to the rat, but in this case it was, and I didn't even notice it till now. It's
You
kinda
can
funny.
just like blur
So-
out the tail over.
We can
there.
pretend like it was like, it was waving so fast that the frame caught it fast.
Genetically mutated.
It could be that
He's a
too.
science rat, so he genetically mutated and have two tails.
All right, well, let's get started, crew. Are we ready? All right, so we're gonna be talking about waves now. We are in the wave theory section. We have moved into full-on physics here, right? Wave theory. So what are waves? All right, so we have mechanical waves that we'll be talking about first, all right? And this is a disturbance in matter, and it carries something from one place to another. What do they carry, Eunice?
A medium.
They go through a medium, but what are they carrying through the medium, Darcy? Vibrations, energy is what we're looking for, but yeah, all right. So they carry energy from one place to another, and a mechanical wave is created when a source of energy causes that vibration, and then Eunice, what does it go through?
Medium.
A medium, that's right. Okay, so what's a medium? Can anybody describe a medium? What is a medium, Eunice? Do you know?
A medium is. A medium.
I don't think you're gonna find it directly in there, just like describe it.
Medium is a repeated back or forth. Like, a medium is the material through which trip.
Yeah.
Travels.
Yeah, could you describe medium without talking about a wave? Nico, can you describe medium? Like without without using a circular definition, so without putting the word wave in it?
Can be moved from its place.
Find it. So what do we mean by, do you want to drink a shot?
A medium is what it doesn't go with the wave.
Yeah,
Like
it goes through it. That's a good way to put it, Darcy. Okay, yeah. So a medium, it could be anything. It could be water, it could be air, it could be a solid, right? So that's basically a medium is just kind of a fancy word for matter that's all the same kind of matter. You know, like say you have a wave and it's going from air to water or water to air, that kind of thing. Then you'd say it was going from one medium to another medium. It's just stuff. It's like a substance, okay? So it's just kind of a fancy way to describe it. All right, so we have different types of mechanical waves. So we have transverse, we have longitudinal, and surface waves, okay? So, yeah, my surfing rats are real fun. I like them. All right, so what's the vibration of a medium at right angles to the direction in which the wave travels? Lewis, do you have that one? Oh, he's looking. You want to throw it to somebody? He's looking. Darcy, what you got?
transfer.
There you go, transverse waves. All right, so at right angles to the direction in which the wave travels. So that means if your medium is like this, think of your medium like a solid, deep, deep wall. Then your wave's at right angles to it, which means it's going this way into the wall that is this way. So there's your right angle. It's kind of hard to visualize, but it'll make more sense in a minute.
That next one, there's
Mhm.
crest, and then the one below it
Is
the
trough, yeah. This is one of those weird words that, yeah, trough, that like a TH is how we say it,
Yeah.
trough, like what an animal feeds out of, a trough, right? Yeah. So you have a crest and a trough. The crest is the high part and the trough is the low part. And then you notice right here at the middle, this little dash line, this is your equilibrium. This is how you're determining your crest and your trough. And truthfully, it kind of depends on your perspective. Remember, we talked about point of reference a while back. We talked about motion. All right, well, if you were upside down to this, then the crest would be the other way and the trough would be the opposite, right? So really what it is those words are there so that you can describe the wave. Because if your perspective changes, then the way you describe it in relation to you is going to change. So that's part of it. Yeah.
When I was in Dolphin Island, we measured the crest. We were doing like a science lab thing. We measured the crest and the troughs.
Outstanding. That is good. All right. So an example would be light waves. So light waves look kind of like this. And we're going to be talking about light in a couple weeks. Light is interesting because light is both a wave and a particle. And we can prove that it works as a wave and a particle. And there's different ways to prove it. And we're going to be doing some of it in lab and it's really cool. But if you're looking at light, which is pretty much if you can see, if you don't have like totally impaired vision, but you're dealing with transverse waves all over the place. Now, there's another kind of wave here, and this is when the medium is running parallel. The vibration of the medium is parallel to the wave. All right, you want to give this one a try, Lewis?
The longitude.
Longitudinal, that's it. All right, so showing a spring is a really good way. You may, yeah, just, I need it back at by 3, so, but don't be out that long. If you, hey, hold on.
Yeah.
If you think too, we could use milk because we're out. And also, and then that wiper situation, if you think about it. If you don't think about it, don't worry about it, okay? Love you, be careful. You got down the car, so, all right, so if you think about this, they have a little like a spring diagram at the bottom, right? That's the best way to kind of picture a longitudinal wave. So if we said, if this is the wall and it's a deep wall, right? The transverse wave goes this way, which means it's going kind of at the wall, it's at right angles. This one is going, this longitudinal wave is going in parallel. So it's like, it goes this way. Instead of this kind of action, it's this kind of action. All right, so what were these going to be? Emma, do you want to do these two? The area where the particles are spaced closer together and the area where they're farther apart. Oh, I thought you had your hand up. If you didn't, that's okay. Oh, yeah. She's looking, she's thinking.
Compression.
Yeah.
And refraction.
Yeah, compressions and rarefactions, exactly. So your compressions are right here and your rarefactions are right here. And you're gonna see this really clearly in lab today because we're gonna be working with slinkies and it's real obvious. Yep.
Those are my favorite.
It makes this super, super obvious. All right, so great example is sound waves. Sound waves are longitudinal waves. So you know how sometimes you can hear a sound wave echo if it bounces off something? Well, that's because it's doing this kind of a thing. So sound wave goes boom, 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 right? And then it bounces back. And sometimes like, if you look at like your speaker, like the button on a laptop, or sometimes like at the bottom of a video, it shows the speaker and then there's like a little curve beside it. And sometimes there's 2 or 3 curves. That's exactly how a sound wave works, right? It's like 1, 2, 3, 4 pushes out like that. So that's why they do that little logo like that. It makes sense.
Do they? Mythbusters did this thing where
I love Mythbusters.
with the speaker and pouring water, and it looks like it's frozen anytime.
I've seen that. Yeah.
And then I have this vibration toothbrush, and I have toothpicks on it, and when I turn it on, it kind of like makes the thing jiggle and just like a word.
Yeah.
I mean, I'm not sure if that's that way, but I can definitely hear it.
Yeah, you can hear the buzzing. Yep. So what kind of wave travels along a surface and it separates two media? It kind of rolls along. All right, Lewis, do you want to give this one a shot? Surface waves, exactly. Okay. So they're like a combination of surface and transverse waves, these love ones and Rayleigh. Mm-hmm. Yep. So if you look right here, these are two versions, a love and a Rayleigh. And you'll see them again in a little bit. But if you look, you can see that you kind of got like a surface wave that moves this way, but then you've also kind of got a transverse wave that sort of goes that way. And the same thing here. So these are a little more complex. So an example would be ocean waves there's a typo. I caught it as they approach the shore. So what you get here is like a rolling thing. So this wave, the actual particles, like the little bits of sand and whatever, are rolling like this as they approach the shore, right? You ever seen anything get sucked into a wave and then it just rolls around and around at the ocean? Yeah. All right, so let's talk about properties of waves. So the maximum displacement of a medium from its resting position, the height or depth of a wave. What do we call this? Darcy.
The maximum displacement,
Mm-hmm.
would be.
The height or depth. So the crest
I don't
or
know.
trough.
Eunice, you take.
Eunice, what you got?
Barely got any.
The maximum
Nico knows. What is it?
Amplitude.
Amplitude. Okay, amplitude. So your crest or your trough is your amplitude. It's the distance from your equilibrium in the middle to either your lowest or highest point. So it's basically how big the wave is this way, right? Especially like with a transverse wave is the easiest way to picture it. So you got a transverse wave. How deep and high does it go from wherever its center point is, right? So the more energy it has, the greater its amplitude. So what's the distance between a point on one wave and the same point on the next one? All right, Emma.
wavelength.
This is
that's
wave-
up there.
There it is. All right. So if you look right here, this is going to demonstrate both wavelength and amplitude. So here's your crest. Here's your trough. This distance, or you could also say this distance, that is your amplitude. Your wavelength, you can measure from here to here, which is easiest. Usually you measure from the top of like a peak or a crest, right?
Wait,
Ye-
does his skateboard, does his thing have a tail? It doesn't.
Actually, I did see this one and I thought it could be that his tail is looped around, so I let that one go. The first one, I just didn't see it all.
I think his tail is broken.
Could
He
be.
broke it while he was.
So your wavelength, so if your amplitude is like how, what was the word we used? The amplitude was how much energy, that's the word we're using, how much energy the wave has, right? Then your wavelength is kind of like how fast it's passing through, but there's another word we use for that. Because this is the wavelength, how far, actually, it's not really how fast, it's how far, how big it is. How fast is, we'll get to that one in a second. Well, here we are. Any motion that repeats at regular intervals is what, Eunice? Frequency. Okay, so that's kind of how fast it's moving. Okay, well, periodic motion and yeah, frequency. We'll do that again in a second. So the time required, I'll give you this one. So period is the time required for one cycle to complete a motion that returns to a starting point. Okay, I'm going to give you an example today where you'll get to see period really clearly with a wave. It'll actually be multiple waves at one time, but you'll get to see period, and then you'll get to see how periods of different waves can align. Waves with different amplitudes will align, and it's really, really, really fun. So the number of complete cycles in a given time, this is your frequency. So this is how fast. So your amplitude is how much energy it has. Your wavelength is how far apart the waves are, and your frequency is like how fast it's going, cycles per second. So what's the unit? Hertz. All right, Hertz is our unit, like the car company. Actually, name for a German scientist. There's a interesting story about Hertz. You could look up his little bio. Actually, I think we talk about him a bit next week. But anyway, your frequency equals the frequency of the vibrating source producing the wave. So frequency right here, you can see like this one's medium, this one's high, and this one's low. If you look at this low one, you can see that the wavelength is further apart. And if you look at all of them though, you'll notice that the amplitude's about the same for all these waves. Okay, So they have the same amount of energy, but different frequency. All right, so if you assume that waves are traveling at a constant speed, then the wavelength is inversely proportional to frequency. So what does that mean? Inversely proportional. Who remembers? Do you remember? Inversely proportional. What's that mean? Inversely proportional. Okay, we have proportional and inversely proportional. What's proportional? Like, what's proportional mean?
Is like the same, so
Yeah.
inverse proportionally would be the opposite of.
Yes, exactly, Emma. So if one goes up, the other goes down. If one goes down, the other goes up. So if you have an increase in your frequency, you're likely to have a decrease in your wavelength. And if you have an increase in your wavelength, you have a decrease in your frequency. Look back at this image at the bottom, okay? You've got, here's your wavelength at the top one, and it's low frequency. So the distance between your wavelength is greater. So your wavelength increased, your frequency decreases. And if you look at that bottom one that says high frequency, you notice the wavelength is very short. The space between each crest is very short. You have a low wavelength, high frequency, okay? So they're inversely proportional. So that's one of those, that's one of those terms that comes up a lot. Inversely proportional. Uh-huh.
Like if someone had, if each person got 3 pennies,
Yeah.
and then they gave 1 penny to them, their thing are purport, or, I don't know how to describe.
Trying to make sense of it.
Yeah,
This is like, do you remember back when we talked about air pressure and altitude?
yes.
Those were inversely proportional. The higher you go, the lower the air pressure, because why? Why is there lower air pressure at high? Do you remember?
Because the oxygen thins out,
Why?
because there are not as many trees and there's no oceans in the sky.
Not trees. There's not as many. Think about, remember, there's a column on your head of all the air molecules. Why is it? Yeah, what? Go ahead. What were you gonna say? Yes, you're right. That's a good way to put it. You can say particles. So if you're on top of Pikes Peak in Colorado, which is a really high mountain, you're on top of a really high mountain, the column of particles, right? The column of molecules that make up the air between you and the top of the atmosphere is much less than if you're down at the ocean. Now that column's longer, so you have more pressure, remember? More particles are pressing on your head. Uh-huh.
When we go to skiing in Utah,
Yeah.
the highest mountain is 10,000 feet. So it's not really hard to read, but when you're skiing up the hill,
Yeah.
it gets way harder to read.
Yeah, and what you were saying about less oxygen, so if there's less particles, and there is less oxygen around, and it's not as, the particles aren't as tightly packed together, and that's where altitude sickness comes from, right? People get sick.
So shouldn't there be more oxygen down at the bottom of the ocean?
Not under the water, but at sea level, yeah. Easier to breathe. Uh-huh.
Like when I went to Colorado for the summer, we drank water.
Yeah, we can get dehydrated. It's really dry there too. All right, so there's actually some cool math here. So this is how this works. So your speed, wavelength, frequency of a wave are related to each other by this type of math. If you were to look at it, you're not going to need it for today, but just so you realize, if you see down here, you have wave speed or velocity, and then you have wavelength and frequency. So we're talking about speed and wavelength. So if I made this, so you can see actually wavelength and frequency together, when you multiply them, you get this kind of this velocity of this wave. All right. So just know that that's a thing. You don't have to do anything with it today. So how do waves interact? Okay, so when an object or a wave hits a surface through which it cannot pass, it's going to bounce back, right? That's how you see things. The light's bouncing off things. So this is called what? Okay, Carlos. Reflection. Just like when you look in a mirror, the light that is on the mirror bounces back at you. You can see your reflection. So an incoming wave can be called, we call these an incident or an incidence wave. So an image, imagine a parallel line connecting to the reflecting surface at right angles. The space created between the incidence wave and the imaginary line is the what? What's that, Darcy?
Angle of incidence?
Angle of incidence, right? Or incidence angles. You can do it either way. On the opposite side of the imaginary line is the reflecting wave bounces away from the reflecting surface, the space between the The imaginary line and the reflecting ray is called, Carlos, what's this one?
Angle of reflection.
There you go, angle of reflection. So you have an incidence angle and an angle of reflection. So if a wave of light comes at a mirror from this angle, it's gonna bounce back at a right angle like this, right? You've seen that, right? Anybody ever taken, like, okay, the back of my phone, where is my phone? The back of my phone, these little guys right here are really reflective. And if I'm in this room or in my bathroom, which is on the back of the house too, in the morning, when the sun is coming through, because it rises right there over the river, and I'm sitting here minding my business, looking at my phone, sometimes a little bit of light will bounce off my phone and into the room, right? It makes like a little spotlight, and my dog goes nuts.
I do that
Oh,
when
I do
I
that
watch.
with my watch.
Yeah, you can use your watch, yep.
I get it in my
Watch
mom's eyes.
phone.
when she's
Speaking
eating.
of reflecting, like, if you're in a bathroom that has a window and there's a mirror.
Oh,
and the
yeah,
light hits it and it makes
Yeah.
a rainbow, they're always so beautiful. I
prisms.
love bathroom rainbows.
yep,
I
yep.
used to have a huge chandelier made of like glass stuff in my old house.
Mhm.
And right around high noon, because we had a huge, like, super tall room, and there was a level there, the chandelier was here.
Yeah.
Space there. When you were walking across there, you were just covered in little rainbows.
Ah, yeah, we're gonna be talking about prisms and light in a little bit too. But yeah, in my dining room, I have that bowl, that big brass bowl, and there's some little balls in it. One of them is covered in little pieces of mirror. In certain times of the year, the sun is just right that it hits that and it makes my whole dining room look like a disco balls going on in there. It's kind of fun. So when a wave moves from one medium into another medium at an angle, it changes its speed as it enters the second medium, which causes it to bend. If you look at this little dude with his fun little beach drink, he is chilling, right? He's got himself a little beach drink. Maybe it's a little cocktail. Maybe it's just soda water and lime. Who knows? So he's got a straw in here. Do you see how the straw, when the light hits it through different mediums, it looks like it's bent, right? It looks like that straw doesn't make a straight line, does it? You ever see that with a straw in a cup of water, glass of water?
I don't know if it's
Mm-hmm.
the same thing, but also fish, when you're fishing, it seems like they're there.
Yeah.
They're there.
Yep, that'll do it sometimes too. Mm-hmm.
When there's this, my grandparents had this little ball that had a ball in it and
Yeah.
looked at a different angle because it was like encased in this glass.
Ah.
Look at a different angle and look bigger and or small.
Mm-hmm. And you can see it. This drink's a little cloudier. It's got more lime juice in here, but you can see it here too. See, the straw looks bigger and out of place. What do we call this? When light waves bend due to a change in the medium, Eunice? Refraction. Okay, so if you have something, and like if you put a straw in a glass of water, the light that's moving through the air only, and you can see the top of the straw sticking out, versus the light that moves through the glass versus the light that moves through the water, is moving through three different types of mediums. So it can make the straw look like it's kind of chopped up or at a weird angle, but it usually doesn't look perfectly straight, and that's why. It's because the light has to travel through a different medium, and that changes how it bounces back at your eyes. So when a wave passes a barrier or moves through a hole in a barrier, it bends and spreads out, just like in a cloud like this. And what do we call that? Louis? Diffraction, right? Okay. So this is also how we get rainbows. Okay. So it has to do with these wavelengths of light being bent in different directions because it's going through something tiny, like in this case, a little water droplet. That's how we get a rainbow, right? All right. So when two or more waves meet, they interact, largely based on how their wavelengths align. So what do we call this, Emma?
Oh,
Oh.
I wanted to say something.
Hang on. Nico.
Interference?
Yeah, interference. What were you gonna say, Emma?
There's this video I have
Uh-huh.
that is about how, like, it's with the diffraction. That's about how we see stars of like little stars and diffraction.
Yeah, we do. There's diffraction involved there. Yeah, play one of those. You could do this with the beach towel, but it works really well if you've ever done one of those parachute activities, like when you're a little kid.
Oh my god.
And they have the big parachute. Right. Now, if everybody goes up at the same time and everybody goes down at the same time, you get this parachute that goes up and goes
You
down.
get to sit on the side, so it stays.
Right. But let me ask you this. If you're doing this with the parachute by yourself and you're creating a wave that goes up and down, and then 5 more people join you, how's it going to impact that wave? Yeah, it's going to be stronger, right? Because now you're like amplifying each other's motion. Now, have you ever done the thing where you throw the ball in the middle and everybody just shakes?
Oh, yeah.
Okay, so those are
We did that.
two types of interference, okay? So one of them is when two waves combine and create a stronger wave. So that's the first one, when everybody's going up and down with the parachute. What do we call that? Eunice?
Constructive.
That's right. That is a constructive interference. So it's good. You're constructing a bigger wave, right? You're meaning together, like congruent, conduct, construct, right? It's together. So you're doing it together and you're getting a stronger wave. Now, what's it called if you're just all shaking like crazy? What's that one, Nico?
Deconstructive.
Yeah, it's a destructive, yeah, it's a destructive wave, which is exactly what it sounds like. Think about that little ball bouncing around on the parachute. That's pretty destructive looking, right? It's bouncing all over, right? And you tend to get a smaller amplitude. So think about that for a minute. The amplitude was the distance between the equilibrium and the crest, or the equilibrium and the trough. When you're constructive and everybody's moving the parachute at the same time, you get a big amplitude, right? But when everybody's shaking crazy like this, what happens to your amplitude? Yeah, you don't get those big up and down, right? You get all these little ones, right? Little ripples. Right. So if the incoming wave and the reflected wave combine in the right places, what do we get then? All right, Lewis. Standing wave, which appear to be standing still. All right, so these points are called nodes and antinodes. All right, so you've got one wave here and a second wave is the dashed line. All right, and when they are exactly perfect like this and they align, it would appear that it's just standing, because you're getting, it looks almost like that. It looks almost like DNA, right? You see how that's kind of does this sort of a deal? Because they're interlacing with each other like this, but it's exactly the same. You will see that today too in lab. It's really cool. You'll see this exact kind of interweaving. It's going to be really neat. Never mind. Okay.
Thank you.
So what always occurs in the same place on a wave near the resting point? Carlos.
Nodes.
Those are the nodes. And then what occur at your maximum points, Carlos? Antinodes, right? All right. So that makes sense. So most objects have a natural frequency at which their particles naturally vibrate. This is probably my favorite image from this slide. So funny. So that's called a resonant frequency. So what occurs when vibrations traveling through an object match its natural frequency, Darcy? Resonance. Okay. So this is fascinating. And we're going to be, you what now?
Oh, Lewis is so good at
I was going to say, you ever done it with a glass? So
With a wine bottle.
you can do that with a glass.
perfect.
The other thing, have you ever seen people, it works with very fine crystal. It doesn't work with like thick, cheap glass. But if you hum at a glass, it will hum back, and it'll hum back at a certain pitch, and that pitch is its resonance. So we're going to be talking a lot next week about how pitch and frequency is what causes pitch. Okay. So we talked about, what was the measurement for frequency? You said it, Darcy. What was the measurement for frequency? Hertz. Okay. So hertz is how we label a particular frequency.
Oh.
So you ever heard an orchestra tune up, like before they play?
No.
They're all sitting down and there's like, and they make all these noises and they all kind of tune. So what they're doing is they're all tuning to a particular frequency. Does anybody know what an orchestra tunes to? It tunes to 440, which is A natural, or A4, which is the A above middle C if you're looking at a piano. So orchestras tune to 440. So 440 hertz is an A natural, and that's where they tune. So if you ever hear that, they're making that weird noise, that's what they're doing. They're all getting to the same frequency. Now, resonance, and there's some really cool stuff with resonance that I'll be showing you. But resonance, everything has its own natural vibration, everything. So like when you hum at a glass and it hums back, you're hearing its resonant frequency. Our organ at church, organs have keyboards, sometimes 3, sometimes 2, whatever. And then they also have a keyboard for the pedals. The pedals is a keyboard. So the organist will use their feet to play as well as their fingers. So they have a lot going on. The low E flat on our organ at church is the resonant frequency of large portions of the building. So whenever our organist hits that, what do you think happens? The whole building shakes. Yeah, if you're in the ladies' room, the stalls will go wah, 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 really loud, and you can't even hear the note in there, but you can feel the shaking. It's really fascinating. I love it. So, seismic waves, we went over these at the beginning of the year. We're just going to touch them real quick. So, when stress in rocks builds up, rocks break or changes shape, release energy, and you get, what do we call these kind of waves? Seismic, everybody together now. So seismic waves include primary waves, secondary waves, surface waves. We've talked about this, right? So this is just a quick review. What do you think this giant wave is?
Tsunamis,
And what causes that?
earthquakes, underwater.
Underwater earthquakes. There you go. So longitudinal seismic waves, I'm just going to go through these. They're called primary waves, okay, or P waves.
Secondary, surface.
Then we get secondary, right, and then surface waves. And then the tsunamis are the big ones. There you go. So we've already gone over this. So this is just like a real quick review. And here you can see your Rayleigh and your Love wave that we talked about before, right? So earthquakes, what's the machine that detects them? Yep, seismograph. And that records the ground movements. All right, now, this dude, some of y'all might not know him yet. All my older kids know him because I use him a lot for chemistry videos too. You'll see him next year if you're around. This is Professor Dave. Professor Dave is like one of my favorite YouTube channels.
I've seen Professor Day.
Yep.
Professor Dave, let's talk about interference and diffraction.
Sir Dave explains. Yeah, this is a lot.
We know a bit about wave mechanics now, so it's time to look at some wave-related phenomena, like what can happen when two waves overlap, or when a wave runs into some solid surface. These are very common occurrences, as we are frequently experiencing sound from more than one location at once, and sound will bounce off of walls and other surfaces. So we need to understand what happens to waves in these scenarios. We know that two solid objects, like two people, can't occupy the same space at the same time. But mechanical waves are not matter. They are displacements of matter that carry energy. So two waves can occupy the same space. And when two waves combine in this way, it is called superposition. When there are two disturbances near one another and their respective series of waves overlap, this is called an interference pattern. And we can see how the regions where the waves intersect generate a completely new pattern. This is easy to see with waves in the water, but sound and light waves also do this. There are a few different things that can happen when interference occurs. Say two individual wave pulses are traveling towards each other, and they have the same amplitude. When these meet, the amplitudes at each point will be added together to produce the respective points on the resultant wave. So there will be a moment where there is one wave with twice the amplitude. Then the two waves continue in the direction they were moving. Each wave maintains its own characteristics before and after the interference. When a resultant wave has greater amplitude than the individual waves, like this case, this is called constructive interference. Now let's say the pulses are on opposite sides of the equilibrium position. Again, according to the superposition principle, we will add the amplitudes to get the resultant wave. But in this case, the two amplitudes add to zero. So the resultant wave will be as though there is no wave at all. Then the waves continue along their trajectories. This kind of interference, where the resultant wave has a smaller amplitude than the individual waves, is called destructive interference. And if the resultant wave has an amplitude of zero, like this example, it is called complete destructive interference. This concept applies to periodic waves as well. First, we can consider two sine waves that are precisely aligned. They are said to be exactly in phase. We can add the amplitudes at every single point, and the result is a similar looking wave with twice the amplitude due to constructive interference, because the crests align with the crests and the troughs align with the troughs. But then, if we shift one of these by half its wavelength, now the crests of one align with the troughs of another. And at every single point on the x-axis, these waves will add up to zero. They are said to be exactly out of phase, and this will be an example of complete destructive interference. This is what noise cancellation headphones do. Small microphones detect background noise and process the associated signal, and then reproduce this noise in a way that is precisely out of phase with the signal. The resulting destructive interference results in zero, or at least dramatically reduced sound waves reaching your ears. In reality, interference patterns are often much more complicated than these two extremes, but in every case, the superposition principle is still applicable. We also want to understand what happens when waves hit a boundary of some kind. If a boundary is free to move, waves will be reflected, bouncing back in the opposite direction, but maintaining the same amplitude. If instead this boundary is fixed, waves will be both reflected and inverted, bouncing back in the opposite direction, but now with amplitude of the opposite sign. Let's say instead of arriving at a solid boundary, a wave arrives at a boundary with a small gap in it. When waves reach an opening like this, they will bend around the edges, producing a phenomenon called diffraction. A diffraction pattern is another kind of interference pattern because of the series of maxima and minima that result, and waves of all types will exhibit this behavior. It was the diffraction of light that provided some of the strangest data we have collected in physics, contributing to the development of quantum theory. But that will have to wait until the modern physics course. For now, let's check comprehension.
We'll skip comprehension. You're good. No, go away. Go away, Professor Dave. Okay, so we don't have time to Mentimeter it, but we will go through these.
Oh.
See what you think real quick. What's that mean? What's that mean? What's that gesture mean? Yeah, hang loose. Yeah. It's actually the Shaka song, which is a Hawaiian thing. It's a Hawaiian culture thing. It's Shaka, and it means hi. It's like hello or shalom or any of those kinds of things, right? All right. So the pinnacle of professional surfing is the ASP World Tour. The Quicksilver Pro is the first stop. Is it in the USA, Brazil, or Australia?
Australia.
Australia. Yep. All right. How about this one? So what's a dagger board? You know?
It's really thin and pointy.
Yeah, it's that little thing underneath this thing. That's a dagger board. Yeah, of course. All right. These are just fun.
Obvious.
These are just fun wave related things. Actually, they're supposed to be figs. I don't know. They showed up for Christmas. How you doing? Okay. So what did Huntington Beach, California become known as? Anybody know what it was called? There's a nickname. It was called Surf City, but we'll skip that page because they're going to sing for you. All right. The dude surfing next to you just called you Barney. Is that a good thing?
No.
No, man. Untalented amateur. So, what's a gurfer or a wahine? Anybody know? It's a girl surfer. You're right. A gurfer. Yep.
I love that picture.
Yep. So, what do surfers call sharks? Do you know?
Sharks.
Surfers have this whole lingo. Do anybody know what they call sharks? They call them men in gray suits. Dude, be careful, man. There's some men in gray suits over there. Have a good day. Right? Yeah. All right. What is a PQRST wave? Does anybody know what a PQRST wave is? Have you ever seen an EKG readout?
Yeah.
That is a PQRST wave. And that's what your heartbeat looks like if you were to put it out as it reads through an EKG machine. So if you were to get a copy of a healthy electroencephalogram, it would look like this. And this little one is PQRST. They call this normal sinus rhythm. So if you ever get an EKG and it looks like this, you're in good shape. If it looks like something else, you might not be, right? All right. How about this? What type of wave is this? Let's watch.
If you don't do the waves, you die.
Let's watch. Oh, look at that. Do you see that?
Ow.
Whee!
let's do it when it comes around to it.
So is that transverse, longitudinal, or surface?
Surface wave.
No, it's transverse.
Why is it transverse?
Because people are going.
Mhm.
Up and down.
So the medium in that case would be kind of like, you think of it like the stands almost, right? And they're going at right angles to it. So that's right. So, whoop, no, I did not know. So then our next one, go to the next one. That's a transverse. I know, he's way cute, right? You gotta love him. So we have to end our surfer lesson with this guy, or wave lesson. You cannot have a lesson on waves without this dude. Y'all seen this dude?
No.
Oh, he's gonna be a surprise.
Running on water.
But the park is still fun, so you'll see kids out there again.
All those kids today, it's just like, dude, you got the best barrels ever, dude. It's just like you pull in and you just get spit right out of them. You just drop in and just smack the lip, pull back, drop down, snap, ah. And then after that, you just drop in, just ride the barrel and get pitted, so pitted like that. Dude, you got the best barrels ever, dude. Just like you pull in, and you just get.
Set it to music.
Further away, and you just drop in and just smack it, pull back, smack.